First of all, also from my side, first of all, thank you very much to have the opportunity to talk here today. It's really a pleasure for me. So yeah, I would, and it fits probably what Dr. Salvagos just has said. I will talk a little bit more about landslide early warning systems, but more in a generic way, more some theoretical consideration and some examples I would like to give. And so what I want to talk, and just very briefly, if I want to talk about landslide early warning systems, I start with landslides, I talk about early warning system, and then I bring it together and then talk about landslide early warning systems. So what we have already seen from all the different pictures and what we already heard, there are different types of landslides that slides down, different materials that are involved. So rock or earth and debris that slides down a slope under the force of gravity. And then we differentiate in different types. So this picture here is a landslide from the Philippines in 2006 that killed 1,200 people in one event, the Ginzagon landslide. And this was, for example, not just one, it was a combination of different, it's called a rock slide debris avalanche. What caused the difference? So we have different types of landslides. We have different cause and triggers. If you think about landslides, or the ground conditions, if it's a hard or a strong rock with fractures inside that can fail, or is it a soft material? We have different processes along rivers that can erode things and make it steeper. Then, as you also heard, rainfall, a lot of rainfall, heavy rainfall that can trigger this, earthquakes. And of course, the humans, and also as we just heard before, where humans building things, how they build things is very important to consider then, and has an impact on the landslide side. And just also to see here is landslides can have different kinematics. They can be different phases of activity, and then they might slow down again, or they just suddenly speed up and fail. They can different run out distances, quite short. So all in all, landslides are quite complex natural phenomena. It makes it quite difficult. And honestly, to be say, we really don't know exactly where a landslide will occur, but we might have indicators where we can look at. So if you think now about what are early warning systems, I would like to use a definition from the UNISDR from 2009. It's a set of capacities needed to generate and disseminate timely and meaningful warning information to enable individuals, communities, and organizations threatened by hazard to prepare and act appropriately and in sufficient time to endure, to reduce the possibility of harm or loss. So a timingful, meaningful information and a warning, people can prepare for it, respond and react to it. And the aim is to reduce, of course, the harm and loss. And as we've already seen, there are different mitigation strategies. Early warning might be one of them. Sometimes you have probably these only ones, but it's not the only one to consider. So in 2006, there was a conference in Bonn, it's the Early Warning Conference 3, where it was discussed how an early warning system can look like in general for different hazards. And this was more on a people-centered focus, but nowadays you also find examples where they use these structure for different scales, where they're looking at these 4 components. This is the risk knowledge, so to understand the hazard, how dangerous is it, what damage it can cause, looking at the people, the vulnerability and exposure, then finding a monitoring tool, device, or technology that enables you to monitor the right parameters, and building a warning service that allows you then to send out these informations that can be then communicated and is disseminated in a proper way so that people understand them, and then in the last can respond to it. What I would like to add to this are some drivers and some important components that are really important if we think about these 4 components. So the first is the user and the stakeholder. So what who is the user? What does he actually want? Is it actually he wants an early warning system, or probably something else? How much does he understand? What are the expectations? Also the environmental setting where we are, what is happening there? Are there changes happening? Climate change we are just mentioning. The social and cultural setting, where does it sit? How much do the people know already about landslides? How do they respond to it? And the institutional setting, more from the communication side, who's responsible for sending out a warning? Is it the stakeholder at all, or do they have other people to be involved in this? I would also to add another button, this is the connect button. So early warning only works if these elements are also connected. And if there's a gap, then this whole system can break. And also, if you have set up these components, it's not ending, it just starts. You have to prove that if things changes, if in an area, we have just heard they build a school or they build roads, does this change your risk? Then you have to look if this change has an impact on your warning system. And so it's a dynamic process that you have to check and improve, and quite time consuming. So if you look now at landslide early warning, so, well, in general, we can say it is the same as an early warning system, but just for landslides. There's an example where I was involved in the Philippines, 2011, where we also looked at a landslide area near this Ginsorgon landslide I've mentioned in the beginning, where we looked at the risk, then tried to find monitoring tools that we can place there, develop a warning service, went out and spoke with people, communication, and also then went to the warning center nearby or along the coast, where they're also looking at other hazards, where we could also place then this system. If I look now at the different elements I've just mentioned, and I don't want to go into detail about the risk assessment because this might be a presentation for itself, but just to mention a few words like what you have also heard before, susceptibility, hazard, and risk. So just to mention this, susceptibility, and I simplified now, how likely is it that a landslide occurs here? Depending on the tools and methodologies you're using, we also talk about probabilistic approaches, so how probable is it? And important that drive the landslide in these areas. From the hazard side, then we look also then how dangerous they are, how often do they occur there, how big are they, how long is the run out? And then in the risk, we also want to understand what can this landslide cause to people, and or can it damage houses, can it destroy things? So how is the exposure, how is the vulnerability? And the data side we have to include in these analysis is also increasing because we implement more informations. It's not only the data, but also the quality we have to include there. So all in this, the risk assessment is itself a quite complex process. From the monitoring side, as I mentioned, so important is to know what parameters we actually want to monitor, and then also to find the equipment to do the monitoring and place the equipment, if it is a local system, in the right spot. So I was involved where they placed the rain gauge suddenly directly around under a tree, where we then said this is probably not the right place. So placing this in the right place, but also having people that are trained in using these instruments and also maintain them. Again, in local systems, everything always has some damages or has to be replaced, or it is old, has to be replaced by newer ones. So you need people to can maintain this. The data received, processed, and should be available and in a meaningful format, and also in real time and near real time. And the data routinely archived, accessible for verification and research purposes. Just to give in the next few slides, just some examples about monitoring from local, but maybe also you can use things on a regional scale. And it's not complete, definitely not, just very briefly. So something like more geotechnical measuring devices you place on the ground or in the ground, like an inclinometer in a borehole. You can measure how cracks are opening, how quick things move. You can also be on the picture before I showed there are two people in the field. If modern technologies allow us not to send people anymore in the field, and I know that Amrita University is doing a lot on these wireless sensor networks and IoT sensors work. I will also give an example later on from one of the early warning sites. So sensors placed in the field that are sending the data automatically, they are connecting each other. So we don't have to go there and get the data out of these devices. We can have geophysical technologies used for this here, like acoustic emission, if there's a movement. In this case, there is then a gravel backfill, but the gravel is then moved if there's a movement, and this can be detected by a sensor. Or we have ERT sensors, electrical resistivity tomography, where we also can measure resistivity changes in the ground. That helps us to get an understanding about moisture changes, what is quite important. And we can also go further away from our landslide and looking more at a bigger area. So we can use laser scanners where we're getting point clouds and can compare it over the time and see if there are some changes. We can use satellite images going much further away from the area that are also not only looking at landslide, but in general changes in the area, land use changes that are important to include in our analysis. Also important, we heard about rainfall, is the monitoring of triggers. So rainfall monitoring is an important part. So placing rain gauges in areas, getting data from the weather observations and include them in our models is a quite important aspect. And to give an example is just one from the UK, from Aldborough. Maybe some of you have heard that in some areas the UK is shrinking, it's getting smaller, just because for the coastal process and the landslide happening there. And one of these areas is Aldborough, where BGS is monitoring for a while now. And it's about 2 meters per, the recession is about 2 meters per year. So we did, or we still do laser scanning, seeing how the coast moves inwards and their houses also and the town. We also have some inclinometers there and piezometers, where we measure then changes over the time and correlate it with weather data to see when we have more movements or when we have less movements. Another example, and I put under monitoring what is not right from the BGS side probably, but for Amrita University, it's definitely an early warning system. But just to put it here, so one system in Munnar, the other one in Gantok, where they used intelligent wireless sensor networks. And BGS came in 2017 and 19, then to also place a PRIME system. PRIME stands for Proactive Infrastructure Monitoring and Evaluation. So they use ERT sensors to see how things, especially moisture and the water moves through time, through the ground, and combining this with the devices from Amrita University. And I don't know if there was already a presentation about this or will be, but I'm pretty sure that colleagues from Amrita can give much more information about this. If it comes now to the warning side, from a technical point, warning is probably not a problem to send out a message, but it's more the question, what actually is a warning? When do we want to warn? Well, probably when something happens that is different from the normal trend. How often do we want to warn? I also said probably always, but this also depends, and I come to this in a minute. And for whom is the warning? Well, this also depends. I also will come to this in a minute. So if we have measurements and we see if something happens that is different, then there's probably something where we are getting, looking at this and we want to do something. Threshold definition. So quite often if it comes to warning, we work with thresholds. This diagram is from a presentation or from work from colleagues from Italy. And there was last week a presentation from Mauro Rossi. So if we develop thresholds, we use quite often a combination of different things. We can model calculations and data analysis based on past landslides, long-term observation of landslide kinematics that we can bring in, knowledge of comparable deformation for such landslides, defined from a behavior of nearby landslides. And quite often important is also the experience of the experts that know more about the landslide in a specific area. And something that I learned, I found it quite interesting, is threshold definition for landslides is a dynamic process. So it's not, if you have defined a threshold, it's not over. Well, the work just starts, because when you're getting more data, when you can improve and refine your threshold, you get a better understanding. So this is not, when you have done it, it's not over. It's just the starting point of the work. And what is also very important in your warning is the warning strategy. So who is warned, when are they warned, and maybe you have different types of warning. So if it is, and I was also headed in projects where it was more a technical issue, it doesn't have to go to everyone. It has to go to the right people that can deal with the technical side. If you have still enough lead time, it's just you observe something, there's probably more for the expert to think about, more as a heads up or preparedness. In some cases, it might be so quick that there must be directly a reaction. And also from my side, when I was involved along the railway lines in Germany, there was just then the point where just if the train has to stop, then there has to be a very quick reaction to the train driver, say, stop the train. So different levels and different actors have to be involved depending on the warning strategy. Also important is the fail-safe system. Early warning systems are 24 hours, 7 days per week, 360 days per week systems, and how many years, however. So they always have to run. And so that's why you need also a backup system. So either you have a power backup that it can run equipment redundancy if something doesn't work, something others can jump in, on-call personal systems, so people that can then help or are trained if one person, for example, leaves, then this person, there must be other people also available. I put false alarm prevention, but prevention just in brackets, because you will not prevent false alarms, but you can reduce them. And you have to communicate false alarms. What does it actually mean to stakeholders, to communities? This is really important. So what you can do is to work on this, to validate your models and your data and all the tools. You can bring in more data, improve the quality of your data. You can check the system reliability, and also using maybe more models, just one model, improve this over the time, bring in information from more devices, so that you can in the end improve also and reduce your false alarms over the time. If we have all this set up, then it's the communication side, and this is quite interesting, I found. So as I said, I'm an engineering geologist, so and when I went out to communities, how can you bring this information to communities that probably have not so much in common with the geology side? So communication is defined as, in this definition here, the process of sending and receiving information among people in an understandable manner. And this is, as I said, it's not going just in one direction, but it's in both directions, where both sides have to come together and find the language they can speak and to understand each other. And this is quite important. So in this context, it is important to understand who are the decision makers. So the function and role and responsibilities for each actor have to be clearly defined, and they have to know who they are and what they have to do. That also messages are guaranteed and ensure that they are receiving the right people at the right time. It has to be tailored to the needs of individual communities and organizations. And warnings have to be specific to the threat and its impacts, and people have to understand them. This is really important. And understanding can also include the language that is relevant. One example is, and also mentioned before, is the Landslip project. I will not go into much detail, just from the communication side, where in this project for 2 test sites in Darjeeling and Nilgiri, different tools were developed, different maps from different susceptibility maps, from the landslide threshold, exceedance, probability models, rainfall forecasts, and weather patterns, the social media and landslide app developed by Amrita. That all goes together on a dashboard, where then the Geological Survey of India do the analysis and interpretation of all these works. And from the communication side, they produce then an information, warning, or forecasting bulletin that goes to the district magistrate. And with the red arrows, just to highlight that it is a chain in the end, to understand what does the magistrate maybe needs, which support can provide it, and also what is not understood, that maybe this can be changed and tailored then. So the last point, response, and I think I don't have to tell much about, because Dr. Sailo-Ghosh has brilliantly talked about the response, what GSI is doing. So generally, they are actions taken more or less directly before, during, or immediately after disaster, in order to save lives, reduce health impacts, and ensure public safety, and meet the basic substance needs of the people affected. So then going out, in this example here in the pictures, is from Scotland, where cars were trapped between 2 landslides, people were evacuated, and then also experts can go out and then map things, speak with people, So all these things on the response side. Oops. So just an example from our BGS side where we were involved in the response work. This was from the Super Typhoon Mangkhut in 2018 in the Philippines, where UNOSAT requested BGS to complete landslide assessment on best endeavors. So we were asked for 3 areas if we can map the landslides and see which areas are more affected. And this is what we have also done. We produced several maps, provided these maps then, so that can be used for the groups in the field and go there and see which areas are more affected. I think that's very quickly my overview. Just to summarize a little bit, so early warning systems are unique because, as I said, depending on which areas you are going, there might be differences, or there will be differences, but some components might be used in other areas and other places as well. And this has to be identified, which can you use, which parameters are similar, then others can take over. And early warning systems are integrated systems of all 4 elements. So that's why I said risk assessment, monitoring, dissemination, preparedness, and response is really important if we talk about landslide early warning systems. Landslides are complex natural phenomena, as I said, and also landslide early warning systems should include then also these 4 elements. What I've not talked about is multi-hazard early warning systems. These exist already, or there are people working on this, but this might be another topic for another presentation. And with this, I stop my presentation and thank you very much for your attention. Thank you.